Hey everybody, welcome back to another round of physics, and yeah, let's keep going. We're delving into the topic of geometric optics, and we've already taken care of the idea about mirrors, and so we should also sit down and talk about lenses. So rather than worrying about reflecting light to bring it into focus, we will use a concept called refraction. So first off, I better start off with something like Fermat's principle to derive Snell's law, or sometimes Snell's law is known as the law of refraction. And then after that, we'll use some time to talk about ray diagrams for lenses. So let's get going. Now, I always thought about this. Fermat's principle, the way that I like to think about it is that, well, case in point right here. Now, this was back when I was in graduate school, but I went to school in Purdue, Lafayette, Indiana. And you'll notice down here at the lower left-hand corner, Purdue is right here. Notice both sides. Okay. And occasionally I would want to drive up and see my mom in northern Michigan, right here. And MapQuest or Google Maps or whatever was the thing at the time, it was always interesting because it would give me two different paths. One of which would basically take me up Highway 65 to Gary, Indiana, and then hook onto other freeway systems and then work my way up the coast. The second one was just a straight shot north, not on a freeway, but rather a state route, and then again, hook on and keep going. And the thing that I always thought about, and I thought, well, yeah, this is Fermat's principle, is that even though I can travel a longer distance, I do it in a shorter amount of time. All right, you can see that even though I travel almost 26 miles further on the right-hand route, the left-hand route, I can get that done in about 10 minutes faster. Okay? Fermat's principle is the same idea. It might be a longer distance, but it's less time. And what happens is that light will follow the path of minimized time, not the path of minimized distance. Okay? So that's Fermat's principle in a nutshell, paraphrased, of course. Light follows the path of least time. Okay? Well, let's go ahead and use Fermat's principle in order to get an equation that describes some of the behavior of lenses. So this is derivation of Snell's law. So let me walk you through the diagram here. First of all, let's pretend for a moment that we have two different materials. Oh, excuse me. There we go. There is my pointer. Let's go to a color that's actually visible. So you can think of this as being some material one. Okay, so think of this as having some permittivity and permeability. And the same thing, I guess I'll subscript that with a 1. The same thing, you have a second material of permeability, permittivity, and permeability. Okay? And the question is, what is the path that minimizes the time if I have a ray of light starting at one location and ending at a different location? So I have zero idea why I chose P and Q here. You could think of this as the starting point and the ending point. Okay. Now I've put some distances in, some variables in, but let's go ahead and work through this. So the first thing I would like to know is the total time that it takes to travel between points P and Q. And you could think of this as divided up into two different paths. The time it takes to travel path 1 plus the time it takes to travel path 2. Which is, okay, you say duh. But now let's go a little bit further. I will go ahead and say that the time that it takes to travel path 1, that is distance d1 on the figure, divided by however quickly the light travels in the first material. Similarly, you could say that t2 is how quickly it travels distance 2 divided by the speed that it travels in material 2. Okay. Well, now let's go ahead and use some of our extra stuff. I would like to parameterize this expression according to the variable x. Okay? So I want to try to get d1 and d2 in terms of x. So first of all, we see that x, as labeled on the figure, is simply the vertical displacement in material 1. And then I have some distance a. So I can rewrite d1 as being the hypotenuse of a triangle, which has a height of x and a width of a. And of course, the Pythagorean theorem tells us that we should have a 1/2 in here. Okay. Similarly, for the second triangle, we can see I called the distance b, and the height here is simply the distance L representing the displacement between points P and Q, minus x being the displacement between point P and the location where my beam of light crosses the boundary between the two materials. So at the end of the day, I have a vertical displacement of L minus x, excuse me, that's not an equal sign, that's a plus, squared plus b squared, the whole quantity square rooted, all over v2. Okay. And so you could say the time that it takes a beam of light to get from location P to location Q is simply given by this expression. Good so far? Nothing fancy, just a little bit of geometry and Pythagorean theorem. Let's go a step further now. Okay. So what we would like to do is apply Fermat's principle. Fermat's principle says that whatever this path is, it is going to do it in the shortest possible time. Now, if I'm trying to find, excuse me, let me go back. If I'm trying to find the shortest possible time, okay, in calculus we would call that an extreme value problem, or maybe a minimization problem. But this is an extreme value problem. I would like to know specifically, if I'm trying to find the time at which this function is minimized, what I should do is take a derivative and set equal to 0. So that's what we're going to do to this expression. We would like to know, this is our function now, and we want to know at what is the value of x for which this time interval is minimized. Okay. Good so far? Okay. So that's what we're doing. Now, hopefully you have this written on the previous page, but you can think about, okay, well, we have to take, well, first of all, the 1 over v1, that's a constant, so we don't have to worry about that. Okay? We had x squared plus a squared in the numerator. Okay? So first of all, I end up with something that says x squared plus a squared, and we have to power rule this. So we get a negative 1/2. So 1/2 comes down in front. So I'll put a 2 in here. And we have to decrease the power by 1. But wait, there's more. Now we have to remember that we have to chain rule. I have a function inside a function. And so we end up taking a derivative of everything inside, and we get 2x. Well, let's go on to the second one. The second one, we have a similar idea. So we have v2, and here we had the quantity L minus x, quantity squared, plus b squared. But again, power rule, we take the exponent, move it down in front, and decrease the exponent by 1. Okay. And then I need to chain rule it. So I need to take a derivative of everything inside here. And so I end up with something that says 2 times L minus x. And we have to chain rule it again. We have the L minus x. So I take a derivative of that, and I get a minus 1. Okay, well, let's go ahead and simplify, right? And don't forget, we want that whole thing to be equal to 0 at the end of the day. So, well, fortunately for us, we see that, oh, goody goody, we'll celebrate our small victories. The 1/2 that's out in front cancels the 2. We also have the 1/2 and the 2. Okay. And we end up with something that says, excuse me, let me go back to red here. We end up with something that says x divided by x squared plus a squared to the 1/2. And I'll leave the 1 over v1 out in front. Okay. And then we have minus, we have L 1 over v2 times the quantity L minus x divided by L minus x quantity squared plus b squared to the square root. Excuse me, to the 1/2. There we go. Now, of course, we want this to be equal to 0 at the end of the day. And we're trying to find a value for x. Or maybe we're trying to find the condition. No, I'm sorry, there's a better way to say that. We're trying to find the condition under which this is true. This equation is true. Good? Okay. Now let's look at this for a second. If I go back to my original figure, okay? If I go back to my original figure, I can look at x over x squared plus a squared, square root, 1/2. Okay. Bear in mind, x is this distance, a is the horizontal distance, and now let's take advantage of the fact that I have labeled an angle in here. And so we recognize that x represents the opposite leg of a triangle. Notice the angle is between the normal and the incoming ray. X is the opposite side, and d1, well, that's x squared plus a squared. I can rewrite this. I could back sub. This is d1. Okay. And we recognize that as simply being the sine of theta 1. Similarly, we have L minus x in the numerator. We had L minus x squared plus b squared, 1/2 in the denominator. That's the same thing as writing L minus x over d2. And if we look, L minus x was the vertical displacement. We have theta 2 in here. That is equal to sine of theta 2. Evidently, by applying the restriction of smallest time, we end up with an expression that says the shortest time that it takes light to travel from point P to Q through the interface between two materials, evidently that occurs when 1 over v1 sine of theta 1 is equal to 1 over v2 sine of theta 2. Okay. Now let me do one other piece of notational change. Now this, in theory, this is we're done. Okay. This would be referred to as Snell's law. Okay. But in practice, it is generally hard to, not generally hard, generally when we're talking about the speed of light through different materials, rather than talking about v, the speed in a material 1, the speed in material 2, usually we use a difference notation. And this is where we come up with the phrase, the index of refraction. So first off, I will say the index of refraction, it's simply a ratio. Okay, so that's the first thing. Historically, the variable n has been used, and the index of refraction is defined as the speed of light in vacuum divided by the speed of light in a given material. And because it is defined as a ratio, you can see that the index of refraction is always greater than 1. Okay. Speed of light is the fastest, that's the speed limit. And so any material, light will travel slower. And so the index of refraction is always less than 1. You can see that if I rearrange for the speed, what this means is that the speed in any given material is given as the speed in vacuum divided by the index of refraction. Okay? Now, of course, instead you could say, well, Greg, can't I just use the permeativity and permeability? Yeah, you could also do that. Theoretically, these two expressions could be used to figure out what the index of refraction is for a given material. So, yes, you could do it that way. I'm going to take this expression and substitute it in. And so what you get at the end of the day is the index of refraction for material 1, sine of theta 1, equals the index of refraction for material 2, sine of theta 2. And this is historically, when you say Snell's law, this is what people are going to be thinking about. Okay? And again, remember, Snell's law comes from the idea that light will follow the path of least time. And if light follows the path of least time, this is the relationship that must be obeyed. Okay? What that means is that sometimes light will travel a farther distance when it can go faster, and then a smaller distance when it goes slower. The analogy I'm thinking of is, for example, if you're running along the beach. If you're on the beach and you're at point P, and then let's see, point Q is in the water. Okay? It is not necessarily, let's say you're a lifeguard, okay? And you need to rescue somebody in the water. Okay? Oftentimes, you don't care about the shortest distance, you care about the fastest time. And so the running straight towards the person, that is a terrible straight line, but you get the idea. Running straight towards the person means that you actually go slower in time. Okay? You can run faster than you can swim, and so you would want to increase the amount of time you spend running on the beach and decrease the amount of time you spend in the water. The, of course, penalty for that is you have to go slightly further distances. Pretty cool, huh? Light is just like a lifeguard. It minimizes the time. It does not minimize the distances. Well, what are some practical applications of this? One that you notice right away is that if you have two different materials, again, material 1 and material 2, those two different materials mean that when light passes from one material to another, it will slightly change direction. And it will change direction according to the indices of refraction. Let me give you an example. Let's say that you're standing above a lake and you're looking down and see a fish. Okay. Now, first of all, the index of refraction for air is very close to that of vacuum. So if we're dealing with air, you can just set the index of refraction to be 1. Okay. That's the first thing. Here, I've given you a second index of refraction, that of water, which is roughly 1.2 or so. Okay. So the first question is, if I draw a line normal to the surface, the question is the angle in air going to be larger or the angle in water? Go ahead, think about that for a second. I will go ahead and write down Snell's law again, just to remind us. Good? Well, you could say, well, how do I get that? You could say if these two quantities are to be the same, so N, let's say that this side is air and this side is water. Okay? If N1 is, if N air is less than N of H2O, the index of refraction of air is less than the index of refraction of water. That means the angle in the air must be larger than the angle in the water. Right? If this is smaller than that, then the sine must be larger than the other sine. So what does this look like practically? Something like this. Is that any ray of light that's emerging from the water, the angle with respect to normal has to increase when it passes into the air. Pretty cool, huh? Well, let's take a step further. I always love this scene in, you're probably familiar, I always love this scene in Castaway, right? So there was a point, I believe, if you've never seen the movie, it's interesting to watch. I don't know if I would watch it 10 times or anything like that. But there's this scene where Tom Hanks gets stranded on an island and he's spearfishing, okay? And I thought the scene was really great because it shows the passage of time without actually telling you anything. So if I recall correctly, there's a scene, Tom Hanks is running around, he's trying to spearfish, and he can never hit the fish. Okay, he's always missing. And then sometime there's like a cutaway scene or a fadeaway scene. And the next scene, Tom Hanks is throwing a spear from a rock from some distance away and bam, hits the fish every time. Okay? And I always thought that was interesting. That first scene, you could say, well, wait a minute. If I think about the light ray hitting my eye, I could say, where does that light ray appear to originate from? Again, assuming you know nothing about Snell's law, you're not thinking about Snell's law at all, from where that image, that light appears to emanate, is not at the fish, right? You could backtrack it. That light appears to emanate way over here. So in reality, although the fish is located closer to you, it appears to be further away. So if you're aiming to hit the fish with the spear, you don't aim for where it looks like it's located at. You have to aim a little bit closer to you. Okay? So again, in the scene, Tom Hanks is trying to spear the fish. He's aiming for where he sees it, not where it actually is. Of course, you see this effect too when you go to say a pet store. If you get right at the edge of an aquarium, you actually get refracted light from two different angles. So one would be, say, the top of the water, the top of the fish tank, and light bends away from normal so that it goes into your eye, and it appears as if the fish were located further away from you. Okay? So over here. But if you get really close to the corner, if you kind of navigate yourself in the right spot, you also get light from the side of the tank, and it will refract into your eye, and it will appear as if there is a second fish in the tank, say, along this line of sight. Okay. And so you get two fish for the price of one. Because of that center fish, the light refracting from that center fish, you get one that seems to be really far away and one closer to the side of the tank. Pretty cool, huh? We can use Snell's law to get an idea about how light will travel through a rectangular prism. So we'll call, or a prism, a rectangular prism, a prism of some sort. So you can think of this as transparent material through light passes very easily. And generally, we will build these prisms with indices of refraction greater than 1. Something like maybe quartz, which I think has an index of refraction of like 1.4. Or some sort of very clear, very transparent type of plastic. Okay. For sake of purposes right now, we'll just assume that n is equal to 1. And again, thinking about Snell's law, as a ray goes from air into a material that has a higher index of refraction, that means that the angle that the ray makes with normal decreases. And so we'll see that according to Snell's law, the angle within the material is smaller than the angle in the air. Okay. Now, for sake of argument, let's go ahead and say that, again, this ray now passes through that face at the backside. Okay. And now that we're going from a high index to a low index, the angle, good, is larger again. So you can imagine that it goes out the backside, and again, the angle that it makes here is larger than the incoming angle inside the prism. Well, how about if I want beam 2 to cross? So that's for beam 1. We can use a triangle to direct beam 1 downwards. How about if I want beam 2 to cross beam 1 somewhere? Well, how should I orient the prism? Yeah. Let's go ahead and flip it upside down, right? And so that second prism will divert the beam 2, upwards so that I can now get the 2 to cross at some location in space, otherwise known as the focus. Yeah, very good. Okay, so we need a focus here. Good. Now you could ask, okay, Greg, what will happen if I make the angle in my triangle more extreme? Okay, and I have to kind of think about limiting cases. Okay, one case is that, okay, the triangle, rather than being a triangle at all, it's going to be a straight up and down. Okay? And so if I send a beam of light through a prism and the beam is perpendicular to the face, what's the deflection going to be as it travels through the material? Yeah, good. Hopefully you see it. Right? If I do n1 sine of 0 must be equal to n2 sine of theta 2. Yeah, good. You see theta 2 is equal to 0. In other words, nothing happens. It just goes straight through. Right? Now, of course, as I start angling that front face, right here, as I start angling that front face, you're going to end up getting some more refraction. Okay. So you start out at 0 and then you get larger as you angle it. Okay? In fact, if you really want, you can go through. This is using a triangular prism, and it's taking the limit as I make the prism more and more skinny, for lack of a better term. So that's what phi represents in this expression right here. How skinny have I made the triangular prism? And we can see that a very skinny prism, phi is equal to 0, you get no refraction whatsoever. And then as you increase it, as you make that triangular prism fatter and fatter, you can see that you can get larger and larger deflection angles. Okay, so I thought I would put that in there. Well, how can we use this to make a lens? How can we use this to focus light? And you've already got the right idea. Okay, let's again say, I'll consider the top piece. Let's again say that I have 4 beams of light, the lowest one being the closest to the optical axis, the top one being the furthest away. So let me draw in an optical axis here. I think I've been doing green. Okay. And so if I draw in the optical axis here, this lowest ray, I need the smallest deflection. And the top ray, I need the largest. So if I'm thinking about a lens arrangement or the triangles, I need the smallest, the least triangular, the most extreme triangle at the bottom, and then more progressively shallower and shallower angles as I get away. And again, the shape is chosen in such a way that every single one of these beams ends up crossing at some final value, some final location in space, the focus. Good. And because these lenses cause a convergence of the rays, this is called a converging lens. Or if you prefer, let's see, this is a convex lens. I usually think of converging and diverging. Well, I've already given away the answer. If I decide, instead of arranging my triangles like this, what happens if I arrange my triangles in the opposite way? Rather than causing these 4 beams of light to converge on a particular location, okay, this arrangement of a prism will cause the beams of light to spread out, to diverge on the opposite side. However, they will diverge if I track back from where those beams appear to originate. They will diverge from, again, a focus, say right there in space. So again, these are called diverging lenses, or these are the concave lenses. Well, I guess I should probably finish up this video with some ray diagrams, again, to help us with kind of qualitatively assessing lenses. So again, like the mirrors, we have three primary rays that we're going to consider. In fact, the first one is exactly the same, okay? With a small caveat. They're exactly the same. First one, parallel to the optical axis, will, rather than reflecting off of a mirror, because we're not dealing with mirrors, we're dealing with lenses, a ray parallel to the optical axis will propagate through a lens and be directed towards a focus. Number one. Number two, a ray that's directed at the optical axis will travel through the lens undeflected. Okay. And the third one will be this is the biggest change. Okay. So rather than talking about the center of curvature, that's a mirror, we are going to talk about a second focus. One of the things perhaps I shouldn't have skipped over is that a lens will have two focal points. One on, for lack of a better term, I'll say the upstream side, and one on the downstream side. So there will be two focuses. We'll deal with symmetric lenses. One on the upstream side, one on the downstream side. Okay? So this third one is talking about using the other focus. So rather than starting at the curvature and going to the top of my object and hitting the mirror, you talk about, I start at a focus, maybe I should say a ray that travels through a focus and strikes the lens will come out parallel. Okay. So slightly different variation than what we did for the mirrors. So make sure you know, if I'm dealing with the mirror, here's the primary rays that I should consider. If I'm dealing with the lens, here's the primary rays I should consider. Okay. Well, let's get some practice. Okay. Let me go ahead. I will go ahead and let's pretend that I have a convex lens. Okay. And here's my optical axis. And now I'll put my lens in the middle. Okay. And the reason that I'm going to put my lens in the middle is that there is a focus both on the left-hand side of the lens and on the right-hand side. Notice I'm trying to keep those focuses equidistant from my center of my lens arrangement. Now, without loss of generality, this is just a demonstrative example. I will go ahead and place my object. I'll say it's outside the focus of the lens. Yes, the position of the object will matter. Okay, so don't assume that an object that's outside the focus will always do this, or an object inside the focus will always do this. Okay, you should do the ray diagram. You should just very quickly sketch it out to get a sense of what's going on. Now, three principal rays. The first one I said, a ray that is parallel to the optical axis. Okay, so I'll draw it here in red. And here I have a convex lens, or if you prefer, a converging lens. Thought there should be an E on there. Okay, well, I guess I'll have to double check. In any case, parallel to the optical axis, passes through the converging lens. It will be directed at the focal point on the downstream side. And it'll carry on its merry way. Okay. Second, well, usually I've been doing this in green, so I'll do it again. The second one is I will take a ray from the top of my object and it will pass through the center of my lens, and it does so, it will propagate through. Now you say, wait a minute, Greg, what's happening? The reality is that there's a little bit of refraction that's happening right there, But because you go through the center and now you notice that this side had a certain way of refracting it, this side has a different way of refracting it, and it turns out that the refraction from the front face cancels out with the refraction on the back face, and it travels through undeflected. Okay. Just thought I would throw that in there. We don't do that, but I mean, like, that's what's going on. That's why it's undeflected. The third piece, and again, you can already tell that you already can make a guess that the image is going to be inverted, and this one looks like it's slightly demagnified, slightly smaller. The third one, of course, is that it travels through. Now notice, I've already used that focus for one of the primary rays. I always used to get confused. Which focus do I use for the third one? What do I do? The issue is that you only use one focus for each primary ray. So if you've already used the downstream focus, you somehow have to use the upstream focus. Okay. So I've already used that one for the red primary ray. So I've got to use the upstream focus for the last one. So here I'm going to draw a line that passes through that focus. It intersects with the mirror. And the third one says, mirror. It intersects with the lens. And the third one says it should emanate parallel to the optical axis. And I apologize. That's not a very good straight line. We'll try that one more time. There we go. Yeah, I finagled it a little bit. I don't have a ruler or anything like that. If you did a ruler, if you did this nice and consistently, making sure the focuses, the foci are equidistant, you'll get the intersection of your three primary rays right here. Okay. So at least I can say that the image is inverted. So it's inverted, upside down. I can say it's real because the actual beams of light truly intersect at that location. And boom, we're done. Well, it's inverted and real. At least for this case, it looks like it's demagnified. Okay. But that one's really close. It's hard for me to tell just off the top of my head. Okay. Which is why in the next video we'll quantify it. So this is good, kind of gives you a rough ballpark estimate, but if you truly need to quantify it, then we can go through and apply the lens maker equation. Good? Well, for sake of argument, let's go ahead and do a diverging lens as well. Again, optical axis. So we'll go ahead, do an optical axis. And here, because it's concave, rather than it bowing outwards, it should concave, so inwards a little bit. So it's thinner in the middle than it is at the edges. And again, I will go ahead and set up two focuses, there and there. And we'll go ahead and put an object in. Good? Go ahead. Draw the three principal rays. Okay, got it? Okay, let's go for it. Number one, okay, we have a ray that is parallel to the optical axis, intersects with the lens. Now, here's the first thing that we have to be careful about. Okay? The first thing is that we have already argued that having such an arrangement should cause the light to diverge, to move away from each other. Okay? So the first tendency is to try to treat it like a converging lens. In other words, taking that and running it through that focus. Okay. Oh, nay. Don't forget, it is a concave lens. It is a diverging lens. That is not how it works. Rather, it moves, the lens will cause the beam of light to shift away from the optical axis. Okay. You say, well, how far away? How do I know how to draw it? Is it just a little bit? Is a lot? How do I know which way to draw it? And the issue is that we cannot use the downstream focus. Rather, we'll use the upstream one. A diverging lens will cause this parallel beam to move away from the optical axis along the line with the upstream focus. So I can pretend to draw a line from the focus to where the beam intersects the lens and continue that line, that is the direction, the path that the beam will follow. Well, how about the center one? The one that goes through the optical center. That one passes through undeflected. Not half bad. There we go. And then we have the third one. Now, remember, I've used the upstream focus now to establish the direction of my first primary ray. So somehow I've got to use the downstream one to get the third ray. And we'll do the same idea, is that we have a ray and it will be directed at this focus. So we go like this. It'll come directed at that focus. And when it intersects the lens, it will be deflected, quote unquote, away from the optical axis. And in fact, it's deflected in a manner that it emerges. So you can pretend it's going towards that focus, but it'll emerge parallel to the optical axis. Now, of course, you can see immediately that on the downstream side of the lens, none of those beams intersect. Hence why we call it a diverging lens. And so the only place for these to intersect, again, we will have to think about where do those beams appear to originate from. So this blue one in particular, we'll have to backtrack it in space. And we see that the intersection of those three rays is right here. Now you notice we had to use the projection of both the red ray and the blue ray. We didn't have to do it for the green one. In other words, even though we had, the green one, actually, the ray actually travels through that location, but the other two only appear to originate from that location. Because of that, this image is still what we refer to as virtual, and we see that it's upright, it's demagnified, and it is virtual. Cool? Okay. Practice that. Keep working at it. Try to get those rules in your head. Because the thing is that after you get this idea about how to deal with the primary rays to figure out where the image is. So, we call this the object. And we call this the image. Okay. Once you get a feel for how to do it for a single lens, okay, or a single mirror, then we can start putting systems together. We can start doing, say, a convex lens followed by a concave lens followed by a mirror. Okay? And you do this the same way that you would eat an elephant, one steak at a time. In other words, you can forget about all of this garbage, right? Forget about that garbage and just focus on doing the primary rays for the first lens element. Once you figure out, say, here's the object, once you figure out the location of the image, then the image for the first lens becomes the object for analyzing the second lens. In other words, you forget about this sucker. This becomes the new object, and you do it again to find the new image location. And of course, the image for the second lens becomes the object for the third lens. And so then you do your analysis again to find the final image location. And so then you have completely analyzed the system of optical elements. Cool, right? Okay, good. I think that's plenty for this lecture. Again, I'll try to hack it down and make sure that, everything's, but that's all I have for lens system. So we'll quantify this with the lens maker equation, And then I think we're probably pretty good for wrapping up the chapter. So in any case, keep up the good work. Thanks for your attention. I'll see you next time.